Before I begin, I'd like to acknowledge that we're on the traditional territory of Tabono, Wurdack, and Euphorbiaceae nations. I myself am Métis Cree from Fort McMurray in Lac-La-Biche, Alberta, so I think it's important to put that acknowledgement out there. So, as said, my name is Warren Cardinal-McTeague. I'm a postdoctoral fellow at the University of Montreal and Montreal Botanical Garden. But today I'm going to talk to you about my doctoral research, which is on diversification of Euphorbiaceae vines. So you're actually in a very rare treat where you have two Euphorb talks in one session, but also two Euphorbs with stinging hairs, so you're getting both genera. I first want to think more broadly why we want to understand patterns of diversification. For one, it provides context about the organisms that we study. For instance, if they've undergone recent diversifications, if they've gone through past extinctions, or if they've evolved relatively steadily through time. It's also important for understanding the processes that generate biodiversity. And in particular, for understanding potential biodiversity gains and losses with respect to climate change. So in the past 10 years, there's been a lot of research on the drivers of plant diversification. And what we know is that it's a combination of both biotic and abiotic factors, and that there's often multiple factors working together. But as we continue pushing this research, we also find that many of these factors are context-specific. So just because you have, for instance, vertebrate pollination, it doesn't mean that you're going to have increases in diversification. So as this research moves forward, we're seeing that a lot of these contexts are important to understand. So my PhD research was on the Euphorbiaceae family. This is one of the largest and most morphologically and chemically diverse plant families. You may recognize some genera, including Cassava, castor bean, ricinus, croton, poinsettia. But perhaps you're most familiar with the succulent and spiky Euphorbias. And so these are the cactus analogs in Asia and Africa. And so despite all this morphological diversity, they're united by a very distinctive synapomorphy, which is three carpellate fruits. They often dry and dehisce explosively, shooting out their seeds. And they leave behind a little persistent columella. So that's a really good synapomorphy across this diverse family. So my research was focused on a specific tribe called Plucaniaceae. And this one is unusual in Euphorbiaceae family for being both having twining habit, but also for mostly having stinging hairs. Normally I drive the stinging hairs home, but today you've seen the other genus. So it's a really interesting, morphologically diverse group, and it's divided into three distinct subtribes. So you have Bellchampia, which has the very enigmatic pseudanthid inflorescences of Bellchampia. It also has stinging hairs. Then you have Plucaniaceae, which has simple flowers and no stinging hairs. And then Trigione, which also has simple flowers but with stinging hairs. So the objective of this study that was part of a broader evolutionary and taxonomic study was to understand the diversification patterns in the tribe. And in particular, we had the opportunity to investigate how overlapping innovative traits interacted. So these are the three traits. So the first one is twining habit. So this is one of the few traits that give plants an element of movement. So they can grow in specific areas and gain access to light or other, access to pollinators or whatnot. It also releases some energy that they would normally invest into structural support because they can rest on other plants. So stinging hairs, of course, is a plant defense, and the idea here is that it reduces herbivory, and over time that could reduce extinction pressures. And then lastly, we have the pseudanthium. And so within this blossom is small unisexual flowers condensed together, and they're subtended by two large involucral bracts. And so it functions as a single flower. And it has this kind of double benefit of being both bilaterally symmetrical, and undergoing specialized pollination biology. So when you undergo selection for floral traits, you can result in genetic isolation and rapid speciation. And so within this tribe, we see a sort of stepwise accumulation of these traits. So you have twining vines, and then a subset that have stinging hairs, and then another subset that have these specialized flowers. And so we hypothesize that the group that has all three of these will have the highest diversification rates. Very briefly, I'll just mention I use a molecular phylogenetics workflow with Sanger sequencing. So we build our alignments, use the nucleotide differences to infer phylogenetic trees, and from those trees, do downstream statistical analysis. In terms of methods, earlier in my dissertation, I had done the first preliminary phylogeny for the tribe. And we had pretty good resolution of the taxonomic groups, but we didn't have very strong support for the backbone relationships. So our major goal was to improve our taxon and molecular sampling with the addition of, say, single copy nuclear genes. And so our diversification analyses, we wanted to be sure to use multiple methods. And so we did tree-dependent with BAM and trait-dependent with HISI. And as my title sort of indicates, we had to think of another aspect that wasn't in our original design, which was biomes. And so for that, we added this recently developed model that includes hidden Markov modeling, and that's GeoHISI. And for that, we divided biomes into sort of wet forested and dry open dominants. And again, our hypothesis was that the more innovative traits we had, the higher diversification rates we would observe. So shown here is our BAM analysis. So that's our beast phylogenetic chronogram, or beast chronogram. And so the colors indicate the different rates of diversification. So blue being rather slow, and then shifts into yellows and reds being increases. And what we see here is that none of these shifts are associated with our traits. So shown here in the background, we see the origin of twining habits, stinging hairs, and our Sudantium. And instead of shifts occurring where we predicted, we see that they're occurring 3 times, almost concurrently around the late Miocene cooling period. And so at first it was a bit of a shock to me because we had sort of invested so much love and energy into understanding these innovative traits. But when we looked more closely, we realized that each of these lineages tended to be very dry dominant, with our outgroups and our early diverging subtribes being more wet dominant. And so that led us to consider that this was maybe due to a shift from wet forests into drier open areas. And so before I move into investigating that, I'll just show you that trait-dependent analyses. So for this, we used a relatively new program called HISI. This includes the hidden Markov modeling, which allows rate shifts to be due to something that's an unobserved trait. So I'm just going to take a quick sip of water. So this figure is kind of a lot to take in, so I'm going to walk you through it. There's 2 colors on each of these branches. On the inside, you'll see a white and a black, and those are associated with the states of each trait. And then the colors on the outside reflect diversification rates, with purples and blues being slow and yellows being fast. And so what we see here, so what I did was we fit 24 different speciation extinction models to each of our 3 traits, and they all recovered this similar pattern, so I'm only presenting stinging hairs here. This is the model average reconstruction, and it really favors a hidden state model, and suggesting that twining, in this case stinging hairs, was not associated with increase in diversification. And in the red dots, those are the same points on the BAM tree as showing where increases were found. And so this smaller figure is just an important illustration because prior to this, we used BISI, which is a binary speciation extinction model. And if we had used BISI alone, we would have recovered a very different conclusion because we would have seen that compared to non-stinging and stinging, there's definitely more species, it must be associated with an increase in diversification. But as we can see, it's actually due to, there was actually relatively constant diversification through this group, and that shifts occurred in a subset that were undergoing different evolutionary processes. So, this was the new addition to our study. That's the area-dependent analyses. So it's very similar to HISI, except instead of a binary state model, we're using DEC biogeography adapted models. And so as you can see here in the tree, it's a little messier than we had originally anticipated. We do tend to see like drier dominance, but there is certainly a lot more variability in biomes than we had anticipated. To walk you through some of our early conclusions, the ancestral biome of the tribe is a bit ambiguous. What we do see is that biome shifts occurred prior to diversification rate increases. So that means it wasn't this beautiful story of a wet forest species moving into a dry dominant area and then immediately taking off. These shifts occurred prior to that happening. And as well, diversification tended to, it only increased in drier open areas, but it didn't occur in every dry open area. So there's all these added contextualities we need to consider when trying to understand diversification in this stage. So in conclusion, I think we're fairly confident that diversification isn't directly associated with innovative traits. What's likely though is that these traits were probably sort of pre-adaptations to doing better in drier open areas. In particular, the stinging hairs, which could deter herbivory from grazing, for instance. We feel strongly that diversification rates are associated with certain drier open biomes. And what's really interesting is that they're all occurring during the late Miocene cooling period. So there does seem to be an element of climate shifts that's important to this story. And so it kind of puts some new context into thinking how plants are going to respond to anthropogenic climate change. Things that aren't diversifying right now may end up being pre-adapted to what will come and diversify from there. And so there's, I'll leave it there. There's lots more if you want to talk to me about this after. I'm very happy to. And I acknowledge my funders, and there were lots of other people who helped this out. So thank you very much.